How's everybody doing? There we go. Yep, good. If you can, please turn on your cameras so that I can see reactions. That'd be great. And before we start, I want to mention that I've been having Zoom problems recently. My computer just freezes for no reason. Sometimes students could still hear me, but what they're looking at on screen is frozen, and my whole computer is frozen, even though sometimes I can still hear you. So if that happens, I have no idea what's going to happen to the recording if it does. But if you can still hear me, but you can't see anything changing on the screen, just let me know. And if you can't hear me or see anything changing on the screen, can somebody just send me a quick message on my phone? Let me know, hey, everything's frozen. That way, I'll probably need to like restart my computer at that point. So, it'll probably be a couple minutes till I'm back in. Sounds good? Am I already frozen? No. Okay, cool. All right. So last time we met, we talked about how, what did we talk about? We talked about how free will can be related to quantum mechanics. Not really. I mean, we talked a little bit about that. I don't know where you go next after talking about a topic like that, but we'll try to beat that. But just for some quick recap, going back a few lectures, we talked about how everything can be described by the time-dependent Schrodinger equation that looks something like this, right? And if you haven't yet, I strongly suggest you sort of memorize that equation, even though you will be given this in tests. I think you should memorize it. And then we talked about how for situations where properties, for example, like energy, the energy doesn't change over time, we get the time-independent Schrodinger equation that looks much simpler, like this. I mentioned that all wave functions are complex, right? Here, there's a complex number I, and here, even though there is no complex number, that wave function can oftentimes be real, there is a complex component, right? That is e to the minus, and I'm going to forget exactly what the form is. Yeah, I'm going to forget what it is. Somebody can remind me. E to the minus I h bar, or et over h bar, I think. Basically, all wave functions have a complex part, even if it's time independent, right? Now, when I first presented this idea of a complex number, somebody asked, well, what does a complex number mean? And I said, well, if you can think of an axis, let's say this is the x-axis, right? And you're plotting the wave function on the y-axis. So maybe your wave function looks like that. If the wave function is complex, you can think of the complex axis as being sort of some other axis that is at right angles to your x-axis, right? And for one-dimensional systems, like just with an x-axis, it's easy to imagine the complex axis going in and out of the page. And the reason why I'm talking about this is because the, there we go. Wait, what are you seeing right now? Oh, are you seeing my screen? Yes, okay. Because the Jupyter notebook that we're looking at, that's due this week, looks at some examples of what a complex axis might look like. So if you look at a wave function where there's a real part and a complex part, and you put them together, right? The complex part here I put in red. It goes sort of in and out of the page, if you can imagine that, whereas the real part goes up and down. But if you sort of plot them, sort of add them up together, you actually get pretty amazing three-dimensional images of complex functions. Complex functions by themselves are very pretty things if you think math can be pretty, but this is just what a simple complex function looks like. And the other thing, here are some more complex ones that I want you to explore, but the other thing that introduces is this idea of movement in the wave function, right? So let me come back to my laptop here in a second. We did the one-dimensional particle in a box. We have a box that goes from 0, x equals 0, to x equals some length a. And outside of the box, the potential here is infinity. And inside of the box, the potential is 0. And in this box, we talked about various wave functions, right? The wave functions must go to 0 at the edges, but inside it does all these fancy loop-de-loops. And it has this form, the particle in a box wave function has this form, psi of n is equal to square root of 2 over a times sine of n pi x over a, where n is some whole number integer, like 1, 2, 3, and so on. Those are all the various types of waves that you can have in this box. In this example that I just drew, n is equal to 2, right? If you had something like this, right, n will be 3, and so on and so forth. But I remember I mentioned that all wave functions are complex, and I'm only drawing one part of that wave function here, right? This is what I'm trying to show you here in this image that you're seeing on the screen. This is one of those wave functions with n equals 3, right? But it's not static. It rotates around because it's complex, and it rotates around at a certain speed, kind of like this. Does that make sense? Does that help you sort of visualize what these wave functions are doing?
So is the imaginary part only present when the wave function is time dependent then?
The imaginary part only appears when you solve the time-dependent Schrodinger equation, yeah? But remember we talked about how even, let me go back to my screen here, even with time-independent ones, there's still an imaginary function part to the wave function. So there's always going to be an imaginary part, but just most times when we're just solving this, most textbooks, when you just solve this equation, it will be all real because they completely ignore this part. And they just completely ignore it because all this part does is do the rotation. That's all it does. This function here is a rotation function. So really, we just draw something static like this in a box. We don't focus on the rotation part because we know that, well, all of them does something like that. Does that all make sense? All right, all of this is very difficult to imagine because we can't see any of this happening. These are all abstract mathematical concepts, right? Because remember I said psi doesn't mean anything. We talked about this. Different people have different understandings of what psi is, but as far as we know, psi doesn't mean anything. All we know is that it contains all information about the particle. I know those two statements seem sort of at odds with each other. The wave function itself doesn't mean anything, but it contains all information that you could ever want about a particle. The only piece of information that actually means something according to our course is this idea that we talked about, I think, last class, which we call the probability density. When you square something like this, the imaginary parts go away, right? Because this means absolute value, and all the negative parts go away, and it just gives you the probability of the wave. That's the only thing, according to what we should know about the wave function, that means anything. The wave function itself doesn't mean anything, but like we see here, it could be, just visualizing it as a graph or something can look amazing. But the meaning of this and where is it rotating and why is it rotating and all that business, like there are lots of scientists trying to figure that out. We don't know. Does that all make sense? Or not make sense? Because that's the whole point. None of this makes sense. We just use it. I see blank faces. All right. If you have any questions about what any of this means, or you want to talk more about it, let me know. But the reason I'm doing the notebook is to sort of give you a feel for what the math actually looks like when you visualize it. All right. Any questions about that? Now, some other things we talked about was this was the probability density, right? And when that is equal to 0, right, when the probability goes to 0, those are called nodes. So nodes are when the wave function probability goes to 0. Another thing that we talked about was what we call quantum mechanical postulate number 5, I think, right? And it's this idea of an average value. So if you take you want to find the average value of some operator, it will be the integral of the wave functions star times that operator times the wave function integrated over all space. Right? So sometimes you can't find the value of an operator in an eigenvalue problem, but you can always find an average value of almost any operator. Is everybody comfortable with that? Cool. And then we talked about how we can find uncertainties in operators. So an uncertainty in any value is a square root of the square of that operator, average value, minus the average value of that operator squared. So this was the expectation or average value, right? And this was the uncertainty. So these are a lot of equations, all of which will be given in exams, but they require lots and lots of calculus, as you can tell just from, this is an integral, and depending on what psi looks like, this equation can be very complex to solve. So if you have, if you do any, I'll put some end of chapter problems for you to solve over the course of the week. If you encounter problems when you try to solve them, just let me know. We can meet, we can discuss them, we can go them over as best as we can. And I'm mentioning all of this because next Thursday is exam 2. And I'm still playing around with the format of exam 2. But I'm thinking what I will do is maybe have some multiple choice questions. Don't know how many, could be one, could be more than one. Some multiple choice questions, and then some long math questions, kind of like what we had in the first exam as well. So it's going to be some combination of this. Essay questions are held to grade, so I might minimize on the essay bits. I'll see. I don't want to write any more essay questions and grade them though. But yeah, so next Thursday will be exam 2, and it'll be on every topic we cover through Thursday of this week, which ideally means we go to the end of chapter 10. If you check our syllabus, we should be closing in on the end of chapter 11 now, but it's all fine. If we're all learning things and this is the pace that works for us, then I'll be great.
Are your exams cumulative, or should we just focus on what we've gone through after exam 1 material?
So the focus is going to be on stuff after exam 1 material, but really at this level, you have to treat everything as cumulative because we're not going to be able to sort of solve this if we don't remember things from chapter 9, for example. But yeah, I want you to focus on things specifically since chapter 9. Basically, let's have the focus be on chapter 10. But that doesn't mean you need to forget everything from chapter 9 because some of those might be important background knowledge, right? Make sense?
Yeah, thank you.
Cool. All right, so we're going to focus on chapter 10. It's going to be some multiple choice questions, some long math questions, and everything through the end of this week. Just as a reminder, we know there are no classes next Tuesday, right? So because it's one of those random break days. So sometime by the end of this week, maybe early next week, I'll post some practice problems there, and we can you can, well, you should practice them, and if you have questions, you'll let me know. But that's all I wanted to talk about for exam 2. Did you have any other, and does anybody have any questions for me about that?
Yes. Aside from the practice problems, are you gonna also put up a study guide just for like the the long questions on the exam?
Yeah, I will try to put up a study guide. But really, it's gonna, I mean, if you, there's only a certain number of problems we can do, because there's only a certain number of things that we can that we've covered. For example, uh, I mean, I haven't written it yet, but I can imagine a question asking you to find the nodes of a wave function, and that might be multiple choice because it's not very math heavy. It's just looking at stuff. But we talked about this kind of finding expectation value. So you can probably expect a question on finding the expectation value of some operator in some wave function. We did uncertainty, so you can probably expect a question on like finding the uncertainty of something if I give you the wave function and the operator. And we did a few of those throughout the semester. So we did problems like, I don't know, find the eigenvalue of some operator, right, on some wave function. So there's only a handful of questions that we can actually do because it's only one chapter's worth of topics, especially for the sort of long math questions that I talked about. But yeah, I will, short answer, I will put a study guide up. Sounds good? Cool. All right. With that out of the way, let's get started on today's material. So when we looked at the particle in the box, right, let's say this is our box, we said that the potential out here was infinite, right? And we only set it to infinity because, let me just write that, the potential was infinite, the potential is infinite. And the reason that we set it to infinity is because we wanted to simplify things. If the potential is infinite, right, the potential energy, V, is infinite, then it means that a particle can't be there, because if the particle is here, let's say, so let's say this is 0 for the wave function. If the particle is not 0 out here, it will have infinite energy because it will have infinite potential energy, right? And we don't like particles with infinite energy, so the particle must be flat out here. It must be 0 out here because the potential is infinite. We don't want infinite potential energy. And because we learned about the fact that wave function must be sort of smooth and continuous, right? Remember some of the properties of a wave function? If it must be smooth or continuous, it can't like start up here and then does its own weird thing like that, because then it's not continuous here, right? So if it must be smooth and continuous, what that means is at the edges of this box, it must start at 0 and then does do its own thing, right? So this was a particle in a box, and then we found all the various solutions for it, but the edges always go to 0. What happens if the potential is not infinite? Because in real life, almost nothing is infinite potential, right? So that's what we're going to talk about now when we talk about quantum tunneling. So what happens if the potential of, the potential of the wall is not infinite? Now, before we sort of tackle this problem with the quantum mechanical system, let's think about what would happen with a more classical system. Remember the hills of a rolling balls, right? Let's say we have a hill. This is my hill. Two hills, right? Let's say this is our ball and we dropped it here. And I let this ball roll. Remember, no friction. This ball will roll down the hill, roll up the hill, but it wouldn't roll past that height, right? Because it doesn't have enough energy. And right, so it'll roll back and roll up and back and forth forever. It will stay inside of that little box, this little valley. Let's look at a slightly different system, right? We have a bigger hill on this side and a lower hill on here. Let's say that continues. If we drop the ball from this height, it will roll down. It has enough energy, so it will roll over the hill and continue forever. So in these systems, the height of the hill was the potential energy, right? And the starting point of the ball was the energy of the ball, right? The starting point of the ball was the energy of the ball. And those are just two situations of what would happen in the real world with macroscopic items. Now let's think of this same setup from a quantum mechanical point of view, right? And instead of having curvy hills, I'm just going to flatten them. So again, we're going to have our potential energy, right? Be some sort of a hill. Let's say out here it's 0. And here there's a potential energy, but it's not infinite. And then it goes to 0 again. And let's say this is the starting energy of the ball, of the particle. The starting energy is lower than the potential energy. So here the potential energy is greater than 0, but not infinity. And here the potential energy is 0, here the potential energy is 0. Right? Kind of like the similar first case where the potential energy here, it's not infinite, but it's higher than the starting energy. Similarly here, the potential energy here is higher than the starting energy. In the first case, the ball will just roll and never go over this hill. In a quantum mechanical sense though, this ball, this wave function would be like kind of like that. But if it ends up somewhere here, it can't just go to 0 immediately, right? Because the wave function, remember, can't be, it can't be multi-valued, it can't be sharp, it must be sort of continuous. So what happens is it continues inside of here. It starts to go down, but slowly. And if it doesn't go to 0 by the edge of the wall, it continues on this side. So let me just repeat what just happened. In the first case of particle in a box, the potential was infinite, so the particle must go to 0 at the edges of the box. And that's it. In this case, the potential is not 0 at the edge of the box. So it doesn't have, the wave function doesn't have to go to 0. It can be any number. But when it reaches the edge of the box, it must decay because there's a potential in here and it doesn't want to be in there because nothing wants to be at high energy. So it starts to decay. And if it doesn't decay to 0 by the end of the box, it continues on. We can think of this as sort of motion. The particle moves towards this wall. Some of it bounces back, kind of like the ball bounces back, but some of it leaks through. And if it's not boggling your brain right now, probably it should. So we have an incident wave. Some of the wave is reflected, but some of the wave is transmitted through.
Is it kind of like how sound goes through a door?
Kind of like how sound goes through a door. You know what? Why not? It's a perfect analogy. Waves do that, right? Except this wave is for a particle. So when you solve this wave, so the blue wave here is the wave function psi, and we said that psi doesn't mean anything, right? So let's look at psi squared, which we talked about, kind of looks like that. I probably didn't draw it perfectly, but the probability density psi squared, that gives us the probability. So if the particle is coming from the left, it has a high probability of being on the left. It has a little bit of a probability of being inside of the barrier, and it has some probability, I probably didn't draw this as nicely as I could. It has some probability of being on the other side of the box. If we go to the analogy here, it's kind of like saying the ball has a high probability of being in this valley bouncing back and forth, but the ball can also be in the mountain, and the ball can also appear on the other side of the mountain, even though it's with low probabilities. In real life, that never happens. The ball would always stay here. The ball doesn't appear inside of the mountain. That never happens. That's weird. The ball never teleports on the other side of the mountain. That's weird. But in quantum mechanics, that can happen. The ball can be on this side of the little barrier that we drew. The ball can be inside of the barrier, and the ball can be on the other side of the barrier. Does that not make sense? Or does that make no sense? The whole thing is weird. I will admit that. But the reason why, sorry, go ahead.
Just to clarify, it specifically can't reach, is it specifically reaching, it can't reach 0 for it to be transmitted, or it can't reach its original starting energy?
It can't reach the, can you
So,
repeat that? I'm trying to.
Sure.
understand.
So you mentioned that as long as the wave as it's going through the barrier doesn't reach, I think you said 0, that it'll be able to be transmitted.
Mhm.
Is it like 0 on the axis, or like 0 compared to where it started? That
0
makes sense.
on the axis.
Okay. Is the starting energy at 0 then? I guess that's what
Um,
I'm confusing myself. I think that's where I'm confusing myself.
the starting energy is not going to be 0.
Okay.
The starting energy will be, I mean, a particle can't have 0 energy, right? That means the kinetic energy is 0 and the potential energy is 0, which means the particle doesn't do anything, doesn't really exist. The starting energy will not be 0. But what I mean by the particle going to 0, I meant the wave function. The wave function doesn't go to 0 at the edge. The value of psi doesn't go to 0.
Okay.
Now, remember, I'm drawing this in 1 dimension, but these waves are sort of 3-dimensional, and there's a complex axis as well, right? That's difficult to draw. So even if it might go to 0 on this axis, it might still not be 0 on the other axis. So it's very difficult for it to go to 0. But the idea here is, while things in real life get stuck where they are, in quantum world, things can teleport on the other side of a wall, even though there might be a wall there. Might be very low probability, but there might be a wall there. And let me show you what that looks like. Nope, there we go. I actually made an animation in here for those of you who've looked at it already of what that looks like. So here, again, I'm not going to go through the math for this. Your textbook actually doesn't go through the math either, or does it? I don't think it does. If you want to see the math for it, we can go through it for sure. It's not that complex. It's just very tedious. And it's sort of reflected in, the math is actually in here if you sort of look carefully. But let's look at this little animation that I made. this is the same situation where we have on the left side, the potential is 0. On the right side, the potential is 0. But in the middle, we have a barrier with a potential that's not 0, right? So if we look at the dashed line, right, there's a wave coming from the left going to the right, and it's hitting this wall. Some of it gets reflected back to the left, right? So that's a dotted line. If you're following my mouse, it's following the dotted line, right? So some of the wave gets reflected back, but some of the wave is able to pass through the box. And when it passes through the box, it appears on the other side. Now you can play around with this if you haven't yet. Let's see, and up here, there's all the way up here, there are different values. E here is the starting energy of the particle. So you can make the starting energy higher or lower, but actually let's see what happens if you make the starting energy 0, like Casey suggested. I have a feeling nothing will happen. Yeah, it's just a flat wave, right? You can't have a particle with 0 energy. So 0 wouldn't work. The particle must need some energy. Remember, the wave is moving, so it must have kinetic energy. So let's change back the energy to 1. So right now, the potential of that barrier is 1.5. What happens if we make that potential 2.5? Let's make the potential higher, stronger, right? Let's see what happens. So if you remember now, the potential is stronger, so less of the wave makes it through. More of it gets reflected back and less of it makes it through. I can make this even more strong, even stronger. Let's go with 5.0. So it's a very strong potential now. And as you can see, very, very little of the wave makes it through. Does that make sense? The other thing that affects the how much of the wave makes it through is the length of the box. So L0 and L1 determines the length. L0 is the left edge of the box and L1 is the right edge of the box. So let's make the box, I don't know, twice as long maybe. The box goes from 0.5 to 3. And let's see what happens. The potential is so strong and the barrier is so wide that nothing makes it through. Do we see that?
So I think part of the confusion, at least I think this is where Casey was coming from, because I'm kind of getting it too, is the 0 potential energy that solid line there, where
it's not shown. It's not shown. The barrier here, the 0 here, this line, this black line, that represents 0 value for the wave function. Remember, the wave function can be positive or negative, right? Like a sine wave, it goes positive and negative. So this line is just the 0 value for the wave function.
So is it not necessarily when it hits 0 value, 0 potential energy, but 0 value for the wave function that it's not transmitted?
Yeah. So when a wave function hits 0 before it reaches the edge of the barrier, it doesn't get transmitted. Like here, it decays down to 0, and then so it never gets transmitted.
Okay, but is the 0 of the wave function, is that 0 potential energy or not necessarily?
No.
Okay.
The 0 here doesn't relate to the potential energy. I sort of use a color code to represent the potential energy. So the whites represent 0 potential energy, and the darker the green in this region, the higher the potential energy. So if I make that potential energy of the barrier 0, right? What I did, you'll see is, what you should see is that green bar disappear, because I basically made the shade of the background the potential energy. It's hard to like show all of these things on the same plot. But look, the barrier now has 0 energy, which means the wave just continues to move unimpeded.
All right, thank you.
Sure. Any other sort of confusion about this? I know this whole thing is not easy to understand. Any other questions about this? Nope. All right, so you can play around with this and see how the various things affect how a particle tunnels. Right, just now we just showed that when the barrier is zero potential, meaning there is no barrier, the particle just continues straight on. Right, everything gets transmitted, nothing gets reflected. Let's change back to, there we go. So you might be asking, or you should be thinking to yourself, well, that's weird, right? I understand you might understand the effect from waves. Okay, it's a wave, it's like sound waves. Sound can come through the door, but bounce back from the door. But if you're thinking of this as like a particle, then that should never happen, right? Like the ball should never be inside of the mountain. It should never be on the other side of the mountain. As long as the energy is larger than the ball should never, the potential energy here is higher than the energy of the ball. The ball should never be on the other side of the mountain. But this effect is very much real and happens a lot in real life. And in fact, one of the places that it does happen is called a scanning tunneling microscope, or in scanning tunneling microscopy. So I'll draw this setup for you. In a scanning tunneling microscopy, and I've worked with lots of friends, collaborators, I guess, who use this setup, though I've never actually used one myself because I probably would have broken it. Usually in a scanning tunneling microscopy, you have a tip made up of some metal and you have some metal surface, right? And these are usually connected to some voltage, right? Voltage. And these things are very, very small. And you have like a molecule or an atom there. And then between that space here is nothing. It's just a vacuum. So I'm going to lay this thing on its side just to sort of, that's the tip, right? That's the vacuum. That's the molecule. And that's the surface, the metal plate. So I just laid it on its side. Now, when you think of potential, remember I said potential from a classical point of view can be thought of as like the height of the mountain, right? So when you think of potential, you want to think of how easy it is for something to be there. If you're on the top of a mountain, you have high potential, but if you're a ball or a person even, it's very difficult to be there because you got to climb that mountain and you got to be up there and it's not very stable. Whereas if you're on a low potential, like in a valley, that's pretty stable, right? You want to be there. You can think of potential as the same way. And here specifically, we want to talk about potential as it relates to where the electron want to be, right? Now, this is a metal, the tip is a metal, and the surface is a metal. Electrons like to be on metals, right? In circuits and stuff. So they will have low potential, right? So if I'm going to draw the potential now, let's say this is the potential energy, right? The tip on here and the surface over here will have low potential. Let's look at the molecule. Electrons, you don't typically want to get added to molecules as often, but they can be on molecules. So the molecule here, right, will have a higher potential than a metal, but it still has a pretty low potential. And now let's think about the vacuum in between. Well, electrons don't want to be in the vacuum. Nothing wants to be in the vacuum, right? So the vacuum will be much higher potential, like that. So if you want to take this scanning tunneling microscopy and translate it into like a system of this hills and mountains and stuff, right? Then the image might look something like this. All right, now let's try to understand what happens. Remember I say that usually these things are connected to a circuit and they apply a voltage, usually very, very tiny voltage, but they do apply a voltage. That voltage gives the electron the starting energy that it needs to go through this system. So if you give it a very low voltage, and again, these voltages are like millivolts and microvolts, I think. Again, I'm not an experimentalist. The numbers might be a little bit off. But if you give the electron a tiny bit of energy, let's say this amount of energy, it might not have enough energy to go through this barrier, right? But if you give it a higher amount of energy, let's say this amount of energy, even though it's not as much energy to go through, like to be in the vacuum, the electron might still have enough energy to tunnel through the other side. Kind of like that. So this is what they do when they do scanning tunneling microscopy. If you have a molecule, let's say you have a molecule shape. So this is the surface. And I don't know, the molecule shape looks like that. Some parts are low, some parts are high, right? And you have the tip right there. If the tip is over here, the barrier is wider, right? So the electron has a lower probability of tunneling through. Whereas if the tip is here, the barrier is narrower, and the electron has a higher probability of tunneling through. So when they scan across this molecule, when they move the tip right across this molecule, they would measure the amount of electrons that pass through. And if you have a lot of electrons passing through, it means that the molecule is very high. If you have a very little electrons passing through, it means the molecule is very sort of low. And from that, you can sort of build a map, atom by atom, of what the molecule looks like using this technology. All they have to do is keep the amount of voltage here, the energy of the starting electron, they keep it constant. Does that make sense? So here's a quantum mechanical technology using a phenomenon that looks ridiculous because it's like particles teleporting on other sides of barriers, even though they shouldn't have enough energy to do so. But they do so because it behaves like a wave, and waves can't just immediately go to zero. Waves have to like slowly decay. And because of that phenomenon, like sound waves and other waves, a little bit of it makes it through on the other side, and we can use that to even like image single molecules. I want to talk about one more place where this idea of electron tunneling comes in, and that is that is for radioactive decay. So let me ask you a question. We know that like charges repel, right? Like positive and positive charges repel, and negative charges repel. So, but we also know that the nucleus of atoms are made up of protons and neutrons really close together. How is it that those protons could be so close together if like positive and positive charges should repel? Does anybody know? Anybody want to venture a guess?
It's the strong nuclear force, right?
Yep. So this is due to the strong nuclear force, which we're not going to go into. But the strong nuclear force forces nuclei together. It's very, very strong force. It overcomes the repulsion force of electrostatic interactions. That's what Coulomb. That's what makes positive and positive charges repel. So if we're thinking about this in terms of potential energy, right? Because of the strong nuclear force, the potential energy would be very, very low, very, very negative when two particles are very close to each other. But then, so very low potential. And then as the particles move farther away, it skyrockets up. So this is the strong nuclear force. Let's not draw it that tall. Let's just draw it here. Let's make that our 0. So this is 0. So this would be negative, and this will be positive up here for our potential energy. I'm only doing that way because negative potential usually means attraction and positive potential usually means repulsion, right? Okay. I think earlier I mentioned that the potential energy for Coulombic interactions, and I'm going to use purple for that, is the charge of one particle times the charge of the second particle over some stuff times r, right? So if the two charges are positive or negative, this potential is positive and it repels. Remember, positive potential means repelling. So, and if r is 0 or very close to 0, this number is very large, and as r goes to infinity, this number goes to 0. So if I were to draw that potential, it might look something like this. Yeah, let's just draw it like that. So this is the Coulombic potential. In case you're wondering what's the x-axis, the x-axis here is distance between, let's say, protons. So it goes from 0 to all the way out to infinity. So when two protons are very, very close, they have very low potential because of the strong nuclear force, but they also have very high potential from Coulombic interactions. And then at long distances, both of those sort of go to 0. If I were to draw these all on the same graph, it would look kind of like this. This strong nuclear force is way, way stronger than that Coulombic potential can ever be. So it's very low. So this is, let's just put V for potential energy. It's very low, but then as soon as it goes a little bit distance away, the Coulombic potential takes over, which is pretty high. And then that goes to 0 slowly like that. Does this make sense, everybody? So I'm trying to draw a map of like the mountains for two protons. And this is sort of the map that you get. Here we have the strong nuclear force. It's only important at short distances. And then at longer distances, here we have the Coulombic repulsion. That's when protons repel because they have the same charge. All right. Now we've been talking a lot about electrons as waves, and really that's what chemistry is. Once we start talking about other stuff, I strongly believe that should be in the realm of physics and stuff. But let's say we have our little proton wave function with this amount of energy. Starting energy of proton, right? So have its energy and it will be in here and it will be happy and all that. Let me just make this cleaner. But this barrier is not infinite in energy. So it will decay. This wave function will decay, but it might have enough to go over on the other side. If you think about probabilities, the probability in here would be large, right? But the probability out here might be very, very tiny, but not 0. Again, I'm not drawing it exactly. So ever so often, right, you try to look for a proton, it will be inside of the nucleus of the atom. But just once in a while, very, very, very rarely, and by random chance, you can find it out here. Just randomly and very rarely. And that whole idea, this whole sort of business is what makes radioactive decay happen. If it wasn't for quantum tunneling, then protons would stay together in the nucleus of atoms. They'll be happy in there because, it's very low energy and the wave function will be just inside of the nucleus. But ever so often, one of these protons has enough energy to tunnel out and be outside of the nucleus. And once it's outside this far away, these two start to repel each other and it moves even further away.
Question.
Yes.
So does the probability, like if we go down to our graph we were on before, once the probability is very low outside of the nucleus, right?
Yes.
But over time, eventually that will happen, right? And
yes.
Once that does happen for the very first time, does the probability sides then flip, I guess, like of the wave function?
So you've asked a very, very, very important question about how this whole thing works. So let me see if I can try to come up with a good analogy here. Because you've asked a very, very important question that's very, very hard to understand. Let's say we have this wave function. This is, right, psi, and let's say that's some x-axis. That's the wave function. If we want to look at the probability, we have to look at the square of the wave function, right? So square, kind of like that. That will be the probability density, psi squared. What that means is, as we talked about, that's a node, probably a node. The particle can never be found there. But then these other spots, you can find the particle. All right, so far so good. We all have this understanding, right? Let's say you look for the particle. You're looking now. Again, people when they talk about quantum mechanics, when they use the word look, they often imagine somebody, a conscious observer like you or me or some other creature, actually searching for a particle, and and that sort of thing. But look here just means interacting with the particle. And let's say we're looking for the position of the wave of the particle. That's what we're looking for. You could look for anything. You could look for the position, you could look for the momentum. You're looking for an observable. Mathematically, what does that mean? If you're looking for the position of the particle, you apply the position operator to the wave function. And if you get a constant times the wave function, this means you can find the position with 100% certainty, right? Like you definitely know where the position is. We all have this understanding, right? Okay. Yeah, no? So this is when we solve these problems, that's exactly what we're doing. We're actually looking for something. We're looking for an observation, right? We're looking for an observable. So if we're looking for the position, we take a position operator, we times it by the wave function, and if we get back something, that's the position. However, if you can't find an eigenvalue problem like this, like you can't find a position, kind of like this, you will still get an answer, but the answer will be random based on the probability. So let's say we can't find this because this equation doesn't work out nicely. It means that we will get an answer, but we don't know what the answer will be. Maybe one time we find it over here, because that's pretty high probability, right? Maybe another time we look for it, we find it over here. Maybe another time we look for it, it's over here, even though that's lower probability, and so on. Does that make sense? So each time we look for it, we might find it at a different spot. And the average of that, we talked about how to find the average value of those. Now let's think of this from the point of view of tunneling. So we have a potential energy, we have zero potential, some barrier, and zero potential again. We put the particle, we shoot the electron from this direction. So we know it's on this side of the box with this amount of energy, right? It must have the same energy. It doesn't gain or lose energy. So it will have the same energy regardless of which side of the box it's on, right? Let's say this is the wave function that we shot. We talked about how it could bounce back, it could reflect, or it could tunnel through and go over on this side. Let's say you look for the particle now, right? And you look for it, and you look for it here, 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 and you didn't find it there, and you didn't find it here, but you found it here. So let's use two different scenarios. And let's use the second time you look for it here, here, and here. You didn't find it here, you didn't find it here, but you found it there. All these numbers are telling you are probabilities, right? So let's say you look for the particle 1,000 times. You might find it 956 times here, but only 44 times over here because it's lower probability. Does that make sense? But let's say we take this one particle that we found over here, and let's try to figure out what it's going to do next. So we know this particle is over here. Again, it has the same amount of energy. The energy doesn't go anywhere, right? Has the same amount of energy. The particle starts here. Let's put it as a single bump, right? With 100% probability. And it then needs to continue on, right? So it will probably continue on and flatten sort of that way. So over time, it will probably look very, very low and flat as it moves off in that direction to infinity. If we wanted to make this a little bit easier to understand, let's say there was a barrier here so that it doesn't go farther away. The particle, we found it over here, and then over time, it will just end up in this box with a small probability of tunneling back over here. Does that make sense?
I think so, yeah. So is it like the whole, I think I've heard a little bit about this before. I'm not sure about anyone else, but is it like that idea that the particle isn't necessarily anywhere until you observe the particle? And then when you observe the particle, it's next, what it does next is now a new, I guess, problem.
Yes. Actually, it brings up something that you've probably all heard about in as it relates to quantum mechanics quite a lot, which is this idea of Schrodinger's cat. Have you guys heard of Schrodinger's cat? Yep. All right. So the idea here is, let's say that's our little particle, that's our little tunneling. Here's our wave function, and it has a small probability of tunneling. And let's do, so that's it, right? When you look for the particle, it could either be over here or over here, right? But on the left side, it has a higher probability than on the right side. But once you've found it, that's where it is. And you start a whole new problem from that. So once you found it, let's say you found it on the left side, now the wave function on the left will look like this with a probability of tunneling back over to the right like this. Kind of like the idea of Schrodinger's cat. right? There's a box, cat's alive, or I don't know, dead. I can't draw cats. Hang on, I could do a better job of drawing cats. You have the box. The cat could be alive. The cat could be dead. But you don't know which until you actually find it. That can be analogous to sort of this system. You don't know which side of the barrier it is until you find it. But once you find it, that's the only answer you can get. Except in this situation, if it's on the right side, it could still always tunnel back to the left side. Again, this whole thing is really difficult to wrap your head around in terms of how it actually works. The wave function itself, like I said, never means anything except possibilities. The wave function doesn't mean anything except possibilities. When you look for it and you find it at one position or the other, this idea here is called the wave function collapse. Right. And there's a couple more ideas that we're going to learn throughout this course, and some of which I think we're going to learn even before the end of the chapter, maybe. That's maybe going to help us understand these things just a little bit more. But yeah, the wave function, again, doesn't mean anything. It just gives us information about what the particle could be doing. When you make an observation, either by specifically finding an eigenvalue or just randomly looking because there is no eigenvalue, you'll get an answer, right? Sometimes you don't know what that answer will be. The answer will just be based on a probability. But once you have that answer, that's where you start with for the next problem. Because so here's one of my pet peeves when people talk about quantum mechanics. I see they're like, some people are like, oh, we don't know whether you're standing on Earth or your wave function is on the moon, right? So you could be standing here on Earth or you could be standing on the moon. Have you guys like heard analogies like that? Maybe, so sort of. And that's sort of true because when wave functions decay, let's say this is a wave function, when it decays, right, it decays very exponentially, very, very slowly to zero. So no matter how far out to infinity you go, it will always get closer and closer and closer to zero, right? Which means that if you have a wave function here on Earth and it decays on the moon, it will be, it'll be very close to zero, but not exactly zero, which means that you have a very small probability of standing on the moon, is what people usually say. But it's a bad analogy because when I look for you, you're on the Earth, right? And your wave function starts over. Basically, your wave function now plots where you are on Earth. Like that probability on the moon has to go back to zero again. I don't know if that makes any sense. So if we search for your wave function, we know exactly where you are. And so this idea that your wave function, yes, it's still minuscule on the moon, but I can see you. You're standing in front of me. You're on Earth. You're not on the moon. Does that make sense? I know this is all very rambly.
One last question on this
Sure.
part, and then I'll be done, I promise.
No,
So
no, that's fine. I like it.
If we go back to our radioactive decay as an example,
Sure.
if we take that nucleus that would be, say we have something that's really prone to decaying, but we in fact completely, this is kind of imaginary, but we completely isolated that thing so no interactions could occur anywhere else. It would never change then because there is no chance for it to interact with something on the other side of that potential energy barrier.
This is another one of those philosophical questions. If there is one electron in the universe, Where is the electron? We don't know. Does it matter? Right? So let's think about it. We have one electron, that's its wave function, right? This is one edge of the universe. This is the other edge of the universe. If we have nothing to interact that electron with, we don't know where it is. The only way we can find out where that electron is to interact something with it, right? Maybe we put a proton here, nothing happens. Maybe we put a proton here, nothing happens. Maybe we put a proton over here, and then all of a sudden, boom, the electron appears over here next to it because the wave function collapsed, and there it is. And the electron circles the proton. If you had no proton there to interact with the electron wave function, then we would never know where the electron is, but then it doesn't matter. The electron exists as a wave throughout the whole universe. The same idea with quantum tunneling, right? So this is our potential barrier, and this is the wave, right? Kind of like that, maybe. There's one proton here, and then there's the other proton that's the wave, right? Because the x-axis is the distance between the two. Theoretically, those two protons are always talking to each other. Protons communicate, all electric particles with charges talk to each other through photons. So they're always talking to each other. So when they're in the nucleus, this proton is always talking to the second proton. I know this is all very, very weird. I like talking about this stuff, but sometimes some of this might be more than you ever need to know. So this proton is always talking to that proton. In a sense, then, this proton is always looking for that other proton, right? It's passing photons, which is light particles, between them, right? So it's always looking for its partner. And sometimes when it looks, it will find it maybe right here. The proton is there, so it's all good. It's there, maybe, it's there, it's there, who knows? But ever so, maybe one time it looks for it, and it's all the way over here, right? It looks for it, and then all of a sudden it's over there. And then when that happens, it's bye-bye proton, because it's not going to come back. I mean, it's probably a very, very, very low probability of that coming back. But mostly it's just, it goes away. So in this case, it's not the case where it's one electron in the universe and there's nothing to interact with it. If you have the strong nuclear interactions, that's because there are at least two protons or two nuclei in there talking to each other at all times. And by talking to each other, I just mean they're always looking for each other. And that's why sometimes I also get a little bit annoyed when people are like, quantum mechanics means you need a conscious observer. No, the protons are always looking for each other. They're not conscious, right? They're just sending signals back and forth. But yeah, so in the case of this, if there's just one nuclei in the universe, they could still decay. It doesn't have to have something else there to interact with it. It interacts with the other proton in the nuclei. Does that make sense?
Yep, thank you.
I love these questions. They're the things that make quantum mechanics strange, but wonderful at the same time. They're weird things that happen just because the math said so. But we've seen all of these things happen in real life through experiments. We've seen radioactive decay. We've used quantum tunneling in scanning tunneling microscopy. So these things are not just like weird mathematical intrigues, right? They're real things that happen in the world that come out of this weird quantum mechanics world. Any other questions about this idea of radioactive decay? A lot of you seem a little bit more lost than usual, or are you not? And that's just your face this morning.
I have questions. I don't know how to formulate them yet. So we'll just wait.
All right. So when you think of them, just let me know. But I mean, we spent a lot longer on this than I wanted to, but that's okay. Because this is the cool thing about quantum mechanics. The math is the boring part. I mean, it's the exciting part too, but it's quite boring. It's what the math can show you. That's quite exciting. So are we losing people or gaining people? I don't know. So let me ask you a more conceptual question then. What? I think I answered my question that I wanted to ask you. But if no living thing existed in the universe, nothing that can see and observe, would everything just exist as a wave scattered throughout the universe with uncertainties, or would things be solid and real, like planets and solar systems and stuff? No living thing, just atoms zipping through the universe as waves. Would planets and solar systems and stuff still exist?
I feel like there would still be planets and solar systems and stuff.
Right, because the atoms are always interacting with each other. It doesn't need somebody to actually look at it to find it. They always interact with each other. That's all. Like I said, that's something that I always get annoyed with when people talk about quantum mechanics in documentaries. I don't want to start a new topic right now. But if I can't think of any other questions, or you can't think of any other questions, I will.
Here's another one, I guess. Is the movement of like from one place to another instantaneous?
I love this question. Okay, so the question is the movement of a particle from one space to another instantaneous? So let's consider a wave that looks like this. And I think, let me just quickly check my notebooks, and I want to see if I did any of this in a Jupyter notebook that I haven't shared with you yet. Just give me a second. So let's say we have this wave. This is our wave function. No, I didn't do one. Okay. So I don't have an animation that I could show you, so we're gonna have to use our imagination. Let's say this is our wave function. So far, we've only ever solved, and we've only ever looked at solutions to the time-dependent Schrodinger equation, time-independent Schrodinger equation, like particles in a box. And we got wave functions like this that tells us the probability. Now, the question was, so this I'm drawing here is psi star, psi, or psi squared, like that, right? That's a probability density. I mentioned that that tells you the probability of finding a particle. So the question was, if you look for a particle and you found it here in trial 1, let's say, and then you look for the particle and you found it over here in trial 2, does the particle instantly, or how fast does the particle move from here to here? Right? Is that sort of the question? Yeah.
Yeah.
Okay. That's not really how it happens. So this is, I can tell you how I think about this problem, right? So in the case of a particle in a box, we have a wave function. Let's say that's the wave function. And each of these waves, right, have a probability. And then you find it at some point or another point And then as soon as you look away, you stop interacting it with something, it spreads out into the wave again. Right? But let's not think about a particle in a box. Let's think about, so this is a particle in a box. Let's think about something else called a free particle. A free particle that moves, it's free to move, nothing stopping it, there is no box, right? Let's say I create an electron at this point, whatever point that is, I create an electron. So when I create the electron, it's right there. Yep. I don't know. Maybe I have some magical powers. I click my fingers. I created an electron right there. My question to you now is, where does the electron move to? Does everybody know? Where does the electron move to? Think about Heisenberg's uncertainty principle. Where does the electron move?
We don't know because we can't know its momentum.
Right. So Heisenberg's uncertainty principle says the uncertainty in the position and the uncertainty in the momentum is greater or equal to h bar over 2. We know the position. So the uncertainty in the position is 0, right? So the uncertainty in the momentum must be infinite. So we don't know if the particle is moving to the left, to the right. We have no idea what it's doing. So what I want you to imagine then, so this is in one-dimensional space, right? This is X. Let's imagine a two-dimensional space with X and Y. And I want you to imagine a surface of a water, like on a pond, right? And me clicking my finger to create a particle at some point is the same as me dropping a stone in a pond at that same point. So now we're thinking two-dimensional. We know where the particle is, it's that point in the pond. We don't know where it's going to move because the momentum is uncertain. So you can think of that particle as rippling out as waves on that pond, spreading in all directions, because we don't know where the momentum is, right? But it can only ever, the wave function can only ever ripple out as fast as the particle can move, and not faster than the speed of light, right? Now, let's say after some amount of time, right, we look for the particle and we look for it over here, 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 right? And each time we looked at it, we didn't find it there or there or there, but we found it here. You collapse the wave function again, so that we know the particle is certainly there, but again, we don't know its momentum. So you can think of it as a new ripple starting out from here and spreading. And eventually you might look for it in a third place and find it here. And then after that point, you can think of it as a new ripple starting out from there. Does that make sense?
Mhm.
So it takes some time to move from one point to another, right? But it's all sort of random and based off of probability where it's going to end up. This picture here is how I can sort of resolve all of this in my head of how the particle moves based off of the wave function. Just think of a surface of water and you're dropping stones. Those are where you're finding the particle. And then it slowly spreads out the wave function. So if I'm looking at it from two dimensions again, right? We found a particle here. After a short time, it starts to spread out. Another short time, it spreads out even more, right? And then eventually it will spread out and look, the wave function will look kind of like that. I wish that we can go into like all the nitty-gritty details of solving the actual time-dependent Schrodinger equation, right? So that we can, because this equation here tells us how the particle will move over time. And that's how we would go from something like this to something like this after a period of time. But it's very complicated math, and it's not math that you need to know. But in terms of imagining what that looks like, just imagining ripples on a pond. Every time you find a particle, it's like dropping a new stone at that point. If you're all sufficiently confused, give me a thumbs up. All right. So I love these questions, and they often raise more. Answering them often raise more questions than they answer. I know that sounds weird, but that's the weird thing about quantum mechanics, because people have been trying to figure out exactly what all this means and how it all works for close to a century now. And it's very difficult to wrap our heads around, because these ideas of waves, the waves itself don't mean anything. It's just mathematics, right? And it's what we can get from the waves that are important. And it's usually why I try to like show you guys these just these little things of what these waves look like and how they move and stuff like that. And so I hope that helps in just like us to imagine these things. But if you have your questions, let me know. And sometimes if all of this is just too much to try to understand, if you're not like nerding out about any of this, that's okay. Just try to focus on the math part of things, right? Because that's more concrete. That's something that you can do, right? Like solving math equations. If you can't, if you don't like to nerd out about the like what does this all mean bit. Sounds good? All right, we'll stop here. We could cover like a quarter of the things I wanted to cover today, which is fine. We'll meet again on Thursday. If you have your questions, let me know. But remember, the Jupyter notebook that I was talking about right here is due Sunday. Next week is exam 2, and I will send some practice problems and a study guide either by the end of the week or early next week. Sounds good? All right. Well, I'll see you all Thursday.